Today we're going to be talking about polar molecules and hydrogen bonding. And polar molecules and hydrogen bonding are going to be extremely important in our everyday lives. Let's first start talking about what a polar molecule is. The best example of a polar molecule is water. So let's go ahead and start with water. H2O, two hydrogens and an oxygen. The atomic number of hydrogen is 1, and the atomic number of oxygen is 8. So using that information, we're going to build a water molecule. So I'm going to go ahead and start with oxygen. Oxygen not only has 8 protons, but if it's electrically neutral, it also has 8 electrons. So I'm going to go ahead and draw the nucleus of my oxygen atom. So P plus protons equal 8. And then I'm going to start adding my orbits. The first orbit holds a maximum of 2 electrons. So 1, 2. And then my second orbit can hold up to 8. However, I've only got 6 left. 1, 2, 3, 4, 5, 6. There we go. Now I'm going to go ahead and add in my hydrogens. Hydrogen has an atomic number of 1, and therefore an electrically neutral hydrogen atom is also going to have 1 electron. So P plus equals 1, and there's my orbit, and I'm going to put the electron right there. Same thing over here. P plus equals 1, there's my orbit, and there's the other electron right there. This is a covalent bond between hydrogen and oxygen. These 2 electrons are being shared, and these 2 electrons are being shared. But because of size and other factors, oxygen does not share the electrons equally with hydrogen. It turns out that fluorine, oxygen, and nitrogen are what we call very electronegative. They have a very strong attraction for electrons. Anytime a fluorine is bonded to a hydrogen, or an oxygen is bonded to a hydrogen, or a nitrogen is bonded to a hydrogen, these are going to be very polar bonds. They're going to be bonds that share electrons, but very unequally. These electrons, because oxygen has a strong attraction or affinity for electrons, are going to be shared unequally. These electrons are actually going to be a little bit closer to oxygen than they are going to be to hydrogen. And because of that, oxygen acquires a slightly negative charge, a delta minus. And hydrogen acquires a slightly positive charge. And again, this hydrogen, slightly positive. Oxygen does not outright steal an electron from hydrogen. However, it does share the electrons unequally. So we got slightly negative, slightly positive, slightly positive. And that's what a polar molecule is. It's a molecule that if we count up all the electrons of hydrogens and oxygen, we get 10. So electrons equal 10. If we count up all the protons, again, we get 10. Same number. It's an electrically neutral molecule. However, if you look at the poles, or the ends of the molecule, slightly positive, slightly negative. That's a polar molecule, a neutral molecule that has slightly positive and slightly negative poles. And because of this polarity, that creates an opportunity for hydrogen bonding. And let's go there next. So I'm going to redraw water in a different way. I'm going to draw water like this. Oxygen connected to 2 hydrogens. And oxygen is a bent molecule. So these hydrogens come off at an angle, about 105 degrees. They don't come off at 108 degrees. So that's what a water molecule looks like. And again, the hydrogens are slightly positive, and the oxygen is slightly negative. Now if I draw another water molecule nearby, same thing applies. Slightly positive, slightly negative, slightly positive. And what we're going to get between this slightly negative oxygen and this slightly positive hydrogen is an electrical attraction called a hydrogen bond. Now it's going to be a very weak electrical attraction, but that's very important. It's very weak, however, there is strength in numbers. Usually hydrogen bonds are present in huge, enormous numbers. And I like to use the analogy of a zipper. If you have a zipper on your coat, each one of the teeth holding the coat together forms a very weak connection, a very weak bond. However, all those teeth together, when you zip up your coat, forms an extremely strong connection. If you try to pull your coat apart, you just can't do it. However, if you try to pull the coat apart one tooth at a time, one pair of teeth at a time, it comes apart very easily. And that is very important. So hydrogen bonds individually, very weak. However, there is strength in numbers, and that's important. Now if we draw another water molecule, there's a hydrogen, oxygen, hydrogen. Again, we get the same weak attraction between this hydrogen and that water. And pretty soon, we've got a whole network of water molecules all lined up due to hydrogen bonding. So hydrogen bonding occurs between molecules, not within a molecule. This is a covalent bond, but occurs between molecules. Now this is going to be extremely important. What are some situations where hydrogen bonding makes a big difference? Well, it turns out that many insects can literally walk on water due to hydrogen bonding. These water molecules form a big net, and when an insect walks on there, these hydrogen bonds, these weak bonds, will actually support an insect's weight. Where else do we see hydrogen bonding? Well, hydrogen bonding is responsible for ice floating on water, for ice being less dense. So that's very important. If in the winter ice sank, everything below the ice would actually be crushed and killed. Hydrogen bonding allows water to be drawn up through trees and plants. Hydrogen bonding allows clouds to form in the atmosphere. So hydrogen bonding is very, very important. In our cells, DNA, hydrogen bonding allows DNA, double-stranded DNA, to be very stable and strong. However, when it comes to replicating the DNA, we can actually unzip or pull apart the DNA very easily because we break one hydrogen bond at a time. So hydrogen bonding, very important.